In a previous video, we introduced a couple oxidizing reagents, a weak one, PCC, pyridinium chlorochromate, and a strong one, and that was written in several different ways, as either chromium trioxide in water, chromic acid, or sodium dichromate or potassium dichromate. Now, in this video, I want to talk about the mechanism for how those work, the story behind how each of those work. Knowing these mechanisms, seeing and understanding these mechanisms will help you to remember how these reagents behave. It will give meaning to their behavior, so they won't just be random letters and numbers that you're trying to keep straight in your head. And that will help you as you get to the end of the course, when there's over 100 different reactions that you'll need to be able to use and combine together and know from memory. Okay, so oxidation, how does it work? Oxidation is really a variation of an elimination reaction. It's sort of a glorified elimination reaction. So let's quickly just review what you need for an elimination reaction. In an elimination reaction, you need a leaving group. The carbon that has the leaving group on it is called the alpha carbon. The one next to that is the beta carbon. And you can have a hydrogen on that beta carbon. That's called a beta hydrogen. In an elimination reaction, you'll have a base, and the base can swoop in, steal that beta hydrogen. The electrons would go toward the leaving group and kick the leaving group off. So here I'm drawing an E2 mechanism, if you remember what that means in that technicality, and if not, I have videos that review that. But notice what you end up getting at the end here is a pi bond. The electrons from this beta hydrogen form a pi bond between the alpha and the beta carbons. Okay, so you form that pi bond there. Now imagine doing that same sort of process, but this carbon, the alpha carbon, being an oxygen. If that were an oxygen, you would start with just one bond to it, you'd end with two bonds to it, that would be an oxidation. So that's what you do when you oxidize alcohols. Now the one thing that's missing here, because you can imagine that that the oxygen here is kind of like the alpha carbon, so you wouldn't really use the term alpha, but you can sort of imagine that it's like the alpha carbon, and then this one would be like the beta carbon, and you have a beta hydrogen there. So we have those ingredients. We're just missing one thing. We're missing a leaving group. We need a leaving group that can take one of these electrons and pull them away and make room for a new bond here. And that is where those chromium reagents come in. The role of those chromium reagents is to act as a good leaving group, to build an attachment to one of these lone pairs and then take it with it as it leaves the molecule, and that makes room to make a second pi bond here. So you could use any of those. I showed in a previous video how those three different strong oxidizing agents can turn into each other. In this one, I'm going to use chromic acid. So H2CrO4. So here is our chromic acid molecule. And the way, again, that's written H2CrO4. But if you have Na2Cr2O7, sodium dichromate, or if you had CrO3 in water, so chromium trioxide in water, they would accomplish this same transformation. I'm going to draw it for chromic acid. Okay, so here you have these two reagents. How do they react? Well, even if you don't know, you know that opposite charges attract. You know that these oxygens here are really electronegative. They pull electron density to themselves, become slightly negative. The chromium loses that electron density, plus it's a metal, so it loses electron density easily anyway. It becomes slightly positive. The oxygen in the alcohol, notice this is an alcohol, the oxygen in that alcohol is slightly negative. And so what can happen as these molecules smash into each other is this lone pair here on the slightly negative oxygen can attack and stick to the slightly positive chromium. Now when it does that, you have to make some room on chromium. If you're going to make a new bond, you have to break one of the bonds that are already there, and the one that breaks is the pi bond. That's the easiest bond to break. Now this step, what we're doing here is we're trying to attach a good leaving group, right? This is going to turn into a good leaving group so that we can do it what would otherwise seem like an elimination reaction. Okay. So here, copy that, and this lone pair now will be to the chromium, which still has one double bond to the oxygen, and now two bonds to OHs, and that last one, that's just going to be a single bond to an oxygen. That oxygen will have 3 lone pairs and a full negative charge. Okay, so that's where we're at after that first step. Now, this negative charge is an unstable part of the molecule. We're going to need that we're going to need to do a proton transfer to that to make that a little more stable. And this oxygen, on what is acting as the sort of alpha carbon, that has a positive charge. Also, notice, because it has 3 bonds. So that gets stabilized by an acid. So you usually have some sort of an acid mixed in with this chromium reagent. Sometimes it'll be sulfuric acid. That's what I'm going to use here. So remember, sulfuric acid is H2SO4. It has a really similar structure as chromic acid, Cr2, or H2CrO4. So you have this sulfur in the middle with 2 OHs on either side and double bond to oxygen up and down. That's sulfuric acid, really strong acid. Okay, so these hydrogens are very vulnerable, they're slightly positive, and if they leave as an H+, the electrons that are left over become a lone pair on the oxygen, and they spread out through resonance because they're allylic over all of these atoms there. So it's a strong acid, it's ready to get rid of the H. The H has a slight positive charge, so when these molecules slap into each other, the oxygen steals one of these hydrogens, the electrons go onto the oxygen there, and you really end up with the same molecule you had, just without that negative charge. So it's a little more stable. Okay. All we've done so far is put a chromium, or a sort of chromate, onto our alcohol, right? We've got the alcohol here, and then the other thing, this group, is just our good leaving group. That's all that is. So if you look at the specific things, it looks complicated and crazy, but conceptually, all it is a leaving group that's going to act just like the leaving group in an elimination reaction. So now we need a base, and here, the base that's often used is water. So notice 2 things that will often be combined with these chromium reagents are sulfuric acid and water. So a recipe for an oxidation is usually one of the chromium reagents, sulfuric acid and water. The oxygen in water is slightly negative, so it can swoop in, act as a base, and steal that beta hydrogen. Those electrons can go toward what we're treating as the alpha carbon, the alpha atom, the oxygen, and they kick this leaving group off. So that's our elimination reaction. You have this sort of beta hydrogen getting stolen, the electrons going toward what you would normally think of as the alpha carbon. Here it's an oxygen, and then it kicks the leaving group off. Now when you do that, you have a few things. First, that chromium leaves, this hydrogen goes onto the water to become hydronium. That gives the oxygen a full positive charge. You have a new bond, a pi bond, between the sort of beta carbon and the oxygen. And that oxygen has a full positive charge because it has 3 bonds now. So this is what we're left with. Now, this chromium reagent, this is sort of a waste product that is not going to participate, this specific molecule is not going to participate in the story of this carbon compound so much right now, so we'll set that to the side. The same for this hydronium molecule. We're focusing in on this carbon molecule, the story of this carbon molecule. It has a positive charge, this oxygen here, so we're not quite safe yet. It's not quite stable yet, so we're going to stabilize that by doing a proton transfer. So we can take another water molecule. The oxygen there has a slight negative charge. The hydrogen here has a slight positive charge. And so the oxygen can swoop in, steal that hydrogen, the electrons snap back onto this oxygen. And notice what we're left with at this point. We are left with 2 things, really. We're left with hydronium. This hydrogen moves over. And the oxygen gains has a full positive charge there. And the other thing we're left with is an aldehyde. And that's really what we're interested in. That's the story of this carbon molecule. It's become an aldehyde. Notice that this really has a hydrogen there. Okay. So we've done an oxidation from an alcohol, what we had originally, to an aldehyde. We did it basically by doing an elimination reaction. All we had to do was put a good leaving group onto that oxygen. That leaving group came from our chromium compound. So the chromium compound is just a fancy way of putting a leaving group onto that oxygen. Ultimately, it takes one of the lone pairs, takes that lone pair with it as it leaves. That makes room for this new pi bond. Okay. So now we have this aldehyde, but notice if we go back to how we were thinking of things, where this oxygen is sort of like the alpha carbon in an elimination reaction, and this other carbon next to it is like the beta carbon, we still have another hydrogen here. If you ever have a beta hydrogen, that means you can do an elimination reaction. And so this aldehyde is vulnerable to being oxidized again. You can oxidize aldehydes again. Compare that with if this were a ketone. So here, I'm separating your mind. I'm just comparing this. I'm pulling this out of thin air. This is not coming from what we were talking about, any molecules from this mechanism. This is just for comparison. Let's say you had this ketone here. Notice that you would not be able to oxidize this ketone anymore. Because if you think of this oxygen as sort of the alpha atom and the one next to it as the beta one, notice there are no beta hydrogens here. You need beta hydrogens in order to be able to do these elimination reactions. If you don't have a beta hydrogen, you can't do the elimination. And here in ketones, there are no beta hydrogens. So that's a crucial point. You can't oxidize ketones anymore. Now, we will see an exception to that later in the course, but for right now, you cannot oxidize ketones anymore. And the reason for that is you don't have any beta hydrogens. Okay. Let's go back to this aldehyde. You can oxidize aldehydes again, but here's the crucial thing. In order to oxidize aldehydes again, you have to have water. This is going to be the big difference between the weak and the strong oxidizing agents. Remember, weak oxidizing agents will stop here. They'll stop at the aldehyde. And they're able to do that because there is no water with them. So notice PCC, and we'll talk about what that is, it stops at the aldehyde because no water is present with PCC. So it's a crucial point. PCC stops here because no water is present. Notice, in these other steps, water is in this solution. If we use chromic acid or sodium dichromate, the strong oxidizing agents, water will be there. And if water is there, water can attack this aldehyde and create what's called a hydrate. So here you have this carbonyl carbon. This carbonyl carbon here. That carbon is losing electron density to the oxygen, so it's ever so slightly positive. Right? The oxygen is pulling the electron density to itself, becomes negative. The oxygen here is slightly negative. And so what can happen is this oxygen can swoop in, the electrons in the lone pair can swoop in, attack that carbonyl carbon, kick the pi bond up onto the oxygen, and you now have a new bond. So you have the hydrogen there still. You now have a new bond to this water molecule. So this has two hydrogens on it. And because it has three bonds now, it'll have a full positive charge. The other oxygen that has only one bond, that'll have a full negative charge. Now you just have to do a couple proton transfers to stabilize this, and you'll have what's called a hydrate. A hydrate is when you have two alcohols on the same carbon. So if you have another water here, I'll draw out the proton transfers here. If you have another water, I'm just going to do this fast. This can steal one of the hydrogens. The electrons snap back onto that. And then this turns into hydronium. This stabilizes the charge on that oxygen. And then you just do one more proton transfer, where this negative oxygen steals this hydrogen here, the electrons snap back here. So notice this in the previous step. You're just moving H's around, H pluses, and you're doing that to stabilize charge. So you move the plus, it's no longer positive. Here we're going to take the negative, we're going to give it the H plus, it won't be negative anymore. Okay, and so we have water, fine, that gets to float around, live its best life in the beaker, and this we have our hydrate. Now the hydrate is crucial. I'm going to erase this one hydrogen here attached to the carbon, just because it's implied in the skeletal structures. The hydrate is crucial because you have these alcohols again. You have these alcohols again, and the alcohols can react with the chromium reagent now in the same way that they did before. Right, so we can take this chromium reagent that we had before, and one of the alcohols is going to attack it just like an alcohol attacked it before. And let me make just a little room here for us to work things out. Okay, so the oxygens in these alcohols, just like before, they're slightly negative. And actually, I'm going to do this, use this one on the top. Either one would work. It's slightly negative, so that's going to be attracted to the slightly positive chromium. The electrons here can swoop in, attack the chromium, just like before. A pi bond breaks, just like before. And what you have now is this oxygen also being bonded to that chromium. Now the chromium is going to have one double bond to an oxygen. It'll have two bonds to OHs. And one bond to an oxygen with only, right, because this was two bonds, but one of the bonds broke. The oxygen will have three lone pairs and a full negative charge. Notice that the oxygen here and the alcohol that attacked has 3 bonds, and so a full positive charge. So this is really, really similar to what we had before, right? When this happened for the very first time. The same attack happened by the oxygen onto the chromium, just like we did. We had this molecule with the positive charge on the oxygen and the negative charge on the chromium's oxygen. And just like before, we're going to do a proton transfer to stabilize that from sulfuric acid, and then we'll be able to do the elimination. Okay. So I'm going to take that sulfuric acid. It's going to do a proton transfer. This negative oxygen swoops in, steals the slightly positive hydrogen there. The electrons snap back onto the oxygen there. And we'll basically have this same structure, just with the negative charge on that oxygen stabilized, right? And this is a principle we'll see over and over again. You can stabilize charge by doing proton transfers. So now what we have is a great leaving group. This is an awesome leaving group, just like before. So we just need a base to come in order to steal our beta hydrogen and do the elimination reaction. Now remember, in these oxidations, the oxygen is acting as the sort of alpha carbon of an elimination reaction. And next to it, you'd have the beta carbon. So here we have this hydrogen on that beta carbon. That's our beta hydrogen. That's the one that the base is going to steal. So you'll have water. The oxygen in water is slightly negative, so that can swoop in, rip that hydrogen off the molecule. The electrons can go toward the oxygen and kick off the chromium, just like before, kick off the chromium leaving group. So that's just like an E2 mechanism, right? Proton transfer and loss of a leaving group. That's an E2 mechanism. Okay, so what we have then, and let me just get this, actually, what we have first is these electrons go onto the chromium. That is a leaving group, and that, like any good leaving group, leaves. Oops. Okay, so that leaves. Now that goes off and lives its own life. To an organic chemist, somebody who's interested in carbon, that would be the gunk that you separate when you do some sort of filtration or crystallization or purification procedure. This hydrogen gets incorporated into what was water, and so now you've got this hydronium wiggling around. And last but not least, these electrons that were to the beta hydrogen will now be to that oxygen. Now that oxygen does have 3 bonds. So this oxygen still has that positive charge there. All you have to do is a proton transfer to stabilize that. We'll do that from water. So the slightly negative oxygen there rips this slightly positive hydrogen off. The electrons snap back onto the oxygen there. And notice what we have here. We have a carboxylic acid. We have a carboxylic acid. And so we've turned this, what was originally just an alcohol, we've turned it into a carboxylic acid. Really by doing 2 elimination reactions. But where one of the atoms, where the pi bond formed to, was an oxygen. So that's oxidation. Now I want to go back to this step here, and I want to talk about what PCC is and how it differs from this. Actually, it's almost the exact same thing. The mechanism is really, truly almost the exact same thing. The reason why you don't oxidize all the way to a carboxylic acid when you use PCC is because there is no water in the slurry of your PCC. That's the whole point with PCC. So PCC stands for pyridinium chlorochromate. Pyridinium chlorochromate. Remember pyridine, we've seen this before. Remember when you were trying to replace an OH with a Cl, you use thionyl chloride and pyridine, the Py, right? This pyridine is going to come back here. If you remember, pyridine is a base. It's a 6-membered ring with a nitrogen in it, and it looks like alternating single and double bonds. Remember, that ring is really, really stable. We'll have an opportunity to talk about that in more depth in a future chapter. But it's really, really stable. The nitrogen by itself has a lone pair, and so it can act as a base. So what this really is an organic base that's really stable. Like this organic part of it will allow it to mix in nonpolar solvents with other organic molecules, but this won't react with anything. Just the base is going to rip hydrogens off of stuff. So that's a base with this sort of stable nonpolar carbon chain. And really the goal here, the unique thing about PCC is you don't use water. So before we used water in the mechanism, you mix those strong chromium oxidizing agents with water. In the case of PCC, you would have chromic acid and you'll mix that with HCl and pyridine. And so what'll happen here is the pyridine is a base, and it will rip the hydrogen off of the HCl. So now you have not pyridine, but pyridinium. Pyridinium is pyridine, but where the nitrogen has an extra hydrogen and a full positive charge. What we also have here is a chlorine lurking around in the solution, a chloride ion, I should say, chlorine with a full negative charge on it. And that can attack chromic acid. So over here we have pyridinium, and that takes the hydrochloric acid and turns it into a chlorine nucleophile. That chlorine with a negative charge then can feel the slightly positive chromium here, swoop in, attack it, one of the pi bonds breaks, and you end up with a molecule called chlorochromate. You have the chromate. Oops. There's only one bond there because the pi bond broke. That puts a full negative charge on this. You have the OH, and now a chlorine. So this part of the molecule, this whole thing, is chromate. The other thing is a chlorine. So that's called chlorochromate. And you'll notice it has a full negative charge on that oxygen that is paired up and stabilized by the full positive charge on pyridinium. And so you end up getting pyridinium chlorochromate, PCC. And the crucial thing is that we made this reagent. This is going to be able to react as a chromium reagent and as a good leaving group, to create a good leaving group in oxidation reactions, just like the chromic acid will. But the crucial thing here is chromic acid is in water, and pyridinium chlorochromate is not. It's in this solution of HCl and pyridine. And because there's no water, because there's no water, once you have the aldehyde, this reaction doesn't happen. You don't form the hydrate. So you don't get the alcohol back, and so you don't have an alcohol oxygen that can attack the chromium to do another oxidation. So it stops here. So PCC stops here. So it's considered a weak oxidizing agent. And the irony is that it really has nothing to do, the chromium itself is the same. The difference is the fact that there's no water there to do this step. And so that's the unique thing about PCC. Okay, if you've gone through this video, what you'd want to take away from this video, what you would want to understand, is first how oxidation reactions are really elimination reactions in disguise. These chromium reagents are just good leaving groups on the oxygen to allow for the elimination reaction. Another thing you should understand is why ketones are not oxidized. There's no hydrogen there for a base to rip off to form a new pi bond. On the carbonyl carbon, there's no hydrogen on that in a ketone. And so you can't use the electrons from it to form a new pi bond. And the last thing you should understand, or a last big conceptual thing you should understand, is why PCC does not oxidize aldehydes. It's because there's no water in that solution that makes up PCC, and so the water doesn't attack the aldehyde to form the hydrate, and if you never form the hydrate, then the oxygen can't attack chromium to get a good leaving group on it and do another elimination to form another pi bond. So hopefully this video has helped clarify the concepts behind how these oxidizing reagents work. They're going to be with us for a long time. In the next, the mechanisms in this video are not things that you would need to be able to draw out for this test. But like I said, knowing the stories and the concepts behind these things are what will save you when you're learning your 99th reaction and trying to keep them all together in your head. So in the next video, we'll go through the exercise and the homework, and we'll see how these oxidizing reagents can be used in synthesis problems.